Welcome to our session on machine learning quantum materials. Today, we are going to see how we can use techniques coming from machine learning to solve open problems in condensed matter physics and quantum materials. And in particular, we will first see how we actually have a relation between finding the many-body wave function of a quantum many-body system and a typical machine learning problem. We will see how some methods for solving quantum many-body wave functions can actually be used for machine learning, and we will finally see how machine learning allows us to combine different techniques that we have in condensed matter physics and quantum materials with machine learning methods in order to solve some problems that are otherwise very challenging. So in particular, today we will see how we can actually use neural networks for quantum many-body wave functions and how we can use these actual neural networks to find many-body wave functions with a finite number of measurements. We will see how we can use a technique from many-body physics known as tensor networks to do supervised learning, so a typical task in machine learning. And we will see how we can use machine learning techniques in combination with very important techniques in condensed matter physics, such as density functional theory, how we can use these machine learning methods to detect phase transitions, both conventional and topological phase transitions, and finally, how we can use machine learning to extract Hamiltonians of quantum materials, so to relate actual measurements to the Hamiltonian of a system. So let us start with machine learning with neural networks, which is one of the most popular methods for actually doing machine learning. One of the important things to note at the beginning is that machine learning is a massive field, and there are many specific tasks that one can try to address with machine learning. Let me just emphasize here three conventional tasks. One is supervised learning. This is the task of wanting to map a certain input to an output. So for example, picture classification problems, they fall in this class. And the way one trains these algorithms is by first providing a set of inputs and outputs. For example, in the case of classifying animals, you provide inputs that are the pictures of the animal, and the outputs are the label of the animal, namely dog, cat, and so forth. And with this label data, you train the algorithm, and when the algorithm is trained, it essentially allows you to classify new images. This is the technique that we can use for classifying states of matter. So instead of giving the picture of an animal, we can actually give a snapshot of a certain material. And this snapshot can be the charge density, can be the local density of states, and so forth. Then there's another very important technique in machine learning that it's generative learning, that it's based on modeling probability distributions. So one tries to find an algorithm that it's capable of reproducing a specific distribution in a very concrete way. And then, of course, there are also reinforcement learning problems in which one wants to create an algorithm that, depending on the state of the environment, takes one decision or another in order to maximize a reward. Today, we are mostly going to focus on techniques related with supervised learning, but let me emphasize that both generative learning and reinforcement learning may allow to solve many other problems that we have in quantum materials. And just to give you a glimpse of why these techniques that are not supervised learning are actually also extremely powerful, let me emphasize here one of the, let's say, most interesting examples that we can have with generative learning, which is the generation of photorealistic images of, for example, cats. So every single one of these images is an image of a cat that does not exist, that has been generated with a GAN, that is a specific type of generative machine learning algorithm. And as I mentioned before, we are not going to go into these techniques today, but we are going to focus on supervised learning. So the idea of supervised learning is that we often need to map an input to an output. And of course, the way in which we map this input to an output is through a very specific function. And this function is what we call a neural network. And this is often referred as a deep neural network. What this actually means is that we have a neural network that it's a collection of nodes and connections. And essentially, these nodes are an array of numbers. which are the input of your neural network. Then you have the next layer, and essentially the value of this node depends on the value of all the previous nodes and the connections that it has. The connections is what we usually call the weights of the neural network, and then you essentially propagate the values of the nodes from one layer to the next layer. So the values in this layer essentially depend on the values that you have in the previous layer and the connections that you have. These connections are usually some nonlinear function. And the basic idea of a neural network is that you essentially have a collection of parameters that are free. And this collection of parameters are usually called the biases and the weights, which are related to how the value of this neuron actually depends on the previous layer. All those parameters are essentially what allows us to parameterize many different functions with the same architecture of a neural network. So with a very specific choice of parameters, we put an input in the neural network and we obtain a very specific output. So in the case of, for example, picture classification, the input of our network would be the whole matrix that essentially is the picture. So all the values of every single pixel. And then the output would be an array that tells us whether if this is a dog or whether if this is a cat. The actual trick of machine learning is that we can actually find very specific parameters for many different tasks. And these architectures that neural networks have allow us to essentially have very complex functions or more simple functions depending on what is the number of layers that we consider. So what we have to do in practice when we have a deep neural network is we need to find the correct parameters of the network to essentially realize the task that we want. And in particular, the way we find these parameters is by minimizing some very specific object that we call the loss function. If you think in terms of a classification problem, then the object that you try to minimize is the difference between the output that you would like to have for a specific input and the one that you actually obtain with the neural network. So when the neural network provides exactly the output that you wanted, then you would call that a minimum. And if the difference is very large, then you would say that the neural network is not properly trained. So for minimizing this actual loss, we use a set of algorithms that very often are based on backpropagation, which is essentially a derivative method. So we minimize the loss just by computing the derivative. And in practice, this is something that we can do in a very, very efficient way with neural networks. So the way that we use this type of neural network is just by thinking about what are the specific inputs and the specific outputs of the different problems that we want to tackle. And in particular, in the case of a classification problem, the input is going to be the image and the output is going to be whether if this is a cat or whether if this is a dog. And so the way in which we usually think about this problem is that we have the picture of a cat, then we have our neural network that when it is trained, is going to tell us that it's a cat. And if we have the picture of a dog, we put it inside of our neural network, then the output is going to be a dog. And the way in which we actually implement this is by saying that, well, the picture of a cat is actually a matrix, the picture of a dog is another matrix, and then whether if it is a cat, if it is a cat, we want to have the output 1, 0, and if it's a dog, we want to have the output 0, 1. So in practice, this becomes a problem of mapping an n times n matrix to a two-dimensional vector. And so we would just need to implement a neural network that gives rise to this sort of architecture. And in this case, what we do is we take that the input layer has the n times n elements, the output layer has just 2 elements, and we take a collection of images that have a label cat or dog, and with this collection of images, we try to minimize the loss function, which in practice can be just the difference between the real value and the expected value. This is the usual way for doing phase classification with neural networks. And this type of problem is, for example, very similar to the problem of actually classifying states of matter. Okay, so now that we know how neural networks work, let us move on to use this type of variational architecture to tackle a quantum many-body problem. So if you think about the typical quantum many-body problem, like for example, the Heisenberg model, then the first important point to notice is that if we have a very large number of particles, so we have a very large number of spins, then the dimension of the problem becomes just too large. So if you start with a typical Heisenberg model like this with L spins, then if you wanted to just store the many-body wave function, you would need to store every single coefficient of the expansion that is here denoted as C. And of course, if you have L sites, then you would have to do the L coefficients. Once L is bigger than 30 or 40, then you do not have actual resources to store all these coefficients, let alone, let's say, finding them. And the idea is that we can actually build a generator of these coefficients without the need of having to store every single one of them. And this generator is actually just a neural network. So the idea is that we essentially say that we want a neural network whose input is the very specific spin configuration S1, S2, S3, SL. You can think that this takes the values up, up, down, up, and all the possible combinations. And then the output of the network is the specific coefficient. So in terms of architecture, this essentially maps a system with L pixels. You can think about it as an image to a single number. And if you think about complex wave functions, then this would be to two numbers. So the real part and the imaginary part. And the idea for this is very similar to tensor networks in matrix product states. In essence, instead of storing every single element of the wave function, we just store a generator of these elements, and we parameterize this generator, in this case, with a neural network. So now the question is, well, how do we find the specific parameterization for the ground state? So we expect that the ground state can be expanded in this way, which can always be, and then the neural network is going to parameterize the state, but we still need to find the actual parameters of the neural network that gives us the right coefficients for the ground state. And the solution for this is actually relatively straightforward, at least on paper. And the idea is that the function that we want to minimize in order to find the ground state is actually the energy of the system. So you can think that the energy is the loss of your machine learning problem. And the energy is effectively computed as the expectation value of the Hamiltonian over the normalization of the wave function. So if you take a neural network and you minimize this object, then you can essentially find the ground state. The ground state parameterized by a neural network. The way in which this is usually done in practice is by saying that every single state of the Hilbert space is essentially going to give rise to an energy that is bigger or equal than the ground state energy. So in practice, if you find the state that has the lowest energy, you are going to find the best approximation to your ground state. And the way in which we usually do this in practice is just by recalling that the wave function is going to depend on many parameters that are essentially the weights and biases of the neural network. And these many parameters can actually, they parameterize both the energy and its derivative. And in particular, if we want to minimize the energy, what we can do is just a variational procedure in which we compute the energy, we compute its derivative, and then we update the value of the parameters so that the energy becomes smaller and smaller. And we do this many, many, many times. And eventually, we will hopefully reach a point in which the derivative of the energy with respect to the parameters is zero. And that would mean that effectively we reached the ground state. And of course, how fast we do this update is what we usually call the learning rate, that it's analogous to the learning rate in machine learning. These neural network quantum states are actually a very versatile set of states. And in particular, we can think that neural network quantum states essentially parameterize a subset of all the quantum many-body states. And in particular, they parameterize a subset that contains other variational quantum many-body wave functions, such as projected entangled pair states, matrix product states, and of course, parameterizations of gapped one-dimensional systems. So neural network quantum states are a very general class of variational quantum many-body wave functions, and in particular, a class that essentially leverages architectures developed initially for machine learning. Now, the very interesting point is that these neural network quantum states actually allow to solve a problem that is very important in quantum physics, which is the problem of quantum state tomography. So let us imagine that you have, for example, a very specific system. It can be a quantum system that has a certain wave function, but you do not know which wave function the system has. Of course, if you have an experiment realizing this wave function, what you can actually do is do a projective measurement that, for example, means that if you have a spin system, you essentially measure the system and see in which direction every single spin is. So sometimes it will essentially go to this state, other times it will go to this state, and other times it will go to this state. So this is essentially a collapse of the wave function. And if you do this measurement many times, you will essentially have a set of, let's say, different states to which the system collapses that effectively gives rise to some statistical distribution. So now the question that you can ask yourself is, if I have this statistical distribution of states to which my system collapses, how can I know what is the wave function of my system? And of course, you would like to know the wave function of your system without making an exponentially large number of measurements. If you have L spins in your system, then you would be tempted to think that you would need at least 2 to the L measurements in order to know all the coefficients of your wave function, or 2 to the L collapses of the wave function to know all the coefficients, but you want to do this with a much smaller number. So the idea is that if you think in terms of expansion of your wave function at a very specific basis, and in particular at the basis in which you perform the measurements, what you very easily identify is that if you want to parameterize your whole wave function, you would need to do the L coefficients here. This is the very same problem as before. And in practice, the probability of obtaining every single state is essentially proportional to the coefficient to the second power. Now, the problem is that you want to get an estimate of all these coefficients at once, but without having to measure all of them. And the idea is that you can do this with a neural network. And the procedure is very similar to actually parameterizing a many-body wave function with the neural network to find the ground state. You take a very specific parameterization of your neural network based on, for example, a Boltzmann machine, or you could use any other neural network architecture. And in particular, you can take a parameterization with 2 neural networks, one that describes the, let's say, absolute value of the coefficient, and another one that describes the phase. And what you actually do is you enforce that this parameterization captures all the different observed collapses of the wave function with the maximum likelihood. And for doing this, you don't need to use actually 2 to the L collapses. You can do it with an arbitrary number of collapses. And so we essentially find the parameterization that maximizes this likelihood, where, let's say, these different terms in the right are actually the measured densities, or the measured states to which the state collapses. And then by doing this minimization, you actually find the parameterization of your wave function. And this is a method that has been observed to be, let's say, very efficient in actually guessing how the wave function looks like. Okay, so far we have seen how we can use techniques from machine learning to solve a quantum many-body system. Now, what we are going to do is just the inverse step. We are going to see how a technique from quantum many-body physics allows us to solve a machine learning problem. And the way to think about this is just by recalling that a many-body wave function is not too different from a large data problem. And again, this boils down to the point that when you have a many-body wave function, you need to determine 2 to the L coefficients. And what you do in many-body physics, in particular when you use matrix product states or tensor networks, is to find a parameterization of these coefficients using, let's say, matrix product states, for example. So in the case of matrix product states, what you actually use is you assume that, let's say, your different coefficients of your wave function can be represented as a product of matrices. So you have, let's say, several matrices per each side, as many matrices as the local dimension. And essentially, if you want to find what is the coefficient for the up, down, up, let's say, configuration, you just take up, down, up matrices, you multiply them, and you will obtain this coefficient. And the deal of this parameterization is that while the dimension on the left is 2 to the L, the dimension on the right is just proportional to the number of sites that you have in the system times the size of your matrix, which is essentially a free parameter that you choose, and it's what we call the bond dimension of the matrix product state. And these matrix product states are usually depicted in this way. So you say that each set of matrices is one node. This would be for site number 1, site number 2, site number 3, site number L. And the different free bonds here are essentially the physical indexes that correspond to the spins, and the bonds that link the different nodes correspond essentially to the index that is summed over in the matrices. And of course, one can use this trick of, let's say, parameterizing a many-body wave function with an exponentially large number of parameters using many different architectures. In the previous case, we considered matrix product states, but you can also start taking the tensors and creating a slightly different architecture in this way, which is called a tree tensor network. You can do it on a, let's say, much bigger scale and create something called multi-scale renormalization ansatz, or you can even do it in a 2-dimensional grid, and this is what it's called projected entangled per states. All these different types of architectures are different ways of parameterizing a very high dimensional object. In the case of tensor network symmetric product states for quantum many-body Hamiltonians, the trick is that optimizing a matrix product state is substantially easier than optimizing a projected entangled per state. But if you think in terms of machine learning or just wanting to parameterize a, let's say, high dimensional object, then in principle, all these architectures could be equally valid. And that is the idea for doing machine learning with tensor networks. So the idea is that the tensor network or the matrix product state, in practice, it is a function that depends on parameters. It maps the coefficients S1, S2, SL to the actual value C, S1, S2, SL. And all the parameters of your function are essentially the different elements of the matrices. So you can think that these different elements of the matrices are now the free parameters for your machine learning problem. And in particular, you can think as if they were parameters of a neural network. And this is what we call quantum many-body inspired machine learning. It's to use a technique coming from many-body physics to do a machine learning task. And let us see how we can actually do this. So for example, if you think about a typical image classification problem, an image is essentially a set of numbers. It's a matrix, an n times n matrix. And what you can actually do is you could take every single pixel of your image and map every single pixel of your image to a 2-dimensional vector. For example, you can think that pixel white is spin up, pixel black is essentially spin in the X direction. And in this way, you could just map your image to a very high dimensional object just by saying that your image is encoded by the tensor product of pixel number 1, pixel number 2, pixel number 3, and so forth. So in this way, if you have n pixels, you are essentially mapping your image to a 2 to the n vector, to an exponentially large vector. And once you make this mapping, you can start thinking whether if you could write down, let's say, an operator in this high dimensional space that realizes the task that you want to carry out, for example, face classification, or let's say image classification, just as a linear operator in this high dimensional space. So in practice, what you do is you map every single image to this high dimensional object, and you ask yourself if there's a linear operator that essentially, when I apply this linear operator to my high dimensional image, it gives rise to essentially the task that I want. If you think about face classification, this would be 1001. So the idea is that, for example, let's imagine that you want to classify clothes. So you want to classify a purse and you want to distinguish it from a shirt. So the image of a purse would be mapped to a very high dimensional object that has 2 to the L coefficient just by this tensor product of every single pixel. Then the same applies to the shirt. And then you could use a tensor network to actually encode the linear operator that you want to apply. So you can take this sort of tensor network that it looks like a tree tensor network. And when you apply this linear operator, you would essentially obtain a lower dimensional object. And then in this lower dimensional object, you can apply a last tensor and essentially get your face classification. For example, 10 for the purse and 01 for the shirt. And this is something that has been done in practice with this very specific type of tensor network. And for the fashion MNIST dataset, that it's a very popular dataset, it actually obtains a very high accuracy that it's actually competitive with conventional neural network algorithms. So the important take-home message is that these variational methods to parameterize quantum many-body wave functions can be understood as another type of neural network. And in particular, you can use these many-body architectures to perform a task that previously they were done with conventional machine learning techniques. Let us now go to a slightly different problem. So this is focused on using machine learning to try to make a step forward in a very important problem in quantum materials that it's related with density functional theory. So when you have a material, many times you actually want to, let's say, solve the whole material not with a model, but by including, let's say, all the electrons in the material, all the nuclei in the material, and so forth. So from this point of view, you essentially think that your material has, let's say, atoms located in very specific places, and that there's some long-range Coulomb interaction between all the electrons in the system, both core electrons and valence electrons, and so forth. And in this type of problem, one usually asks the question, well, what is the many-body ground state of my system? And this is, of course, a very challenging question. So it is the most challenging problem that we can think of. But you can ask a different question, which is, what is the ground state density of my material? And in particular, can you find some way of mapping the Hamiltonian to the ground state density without actually going through the wave function? And this is the idea of density functional theory. Density functional theory is essentially based on the fact that there's a mapping between the Hamiltonian and the electronic density. So in practice, usually we have this typical Hamiltonian for electrons in a material. So we have the kinetic energy of the electrons, we have the interactions between, let's say, the electrons and the nuclei, and then we have the interactions between electrons. And this type of Hamiltonian has a very, very complex many-body wave function that looks like this. And in particular, the electronic density is obtained when you integrate over all the coordinates except the last one. So in density functional theory, instead of focusing on the wave function, we just focus on the electronic density. And we essentially try to think whether if there's some mapping between the Hamiltonian and the electronic density. And this is actually supported by a very important result, which is called the Hohenberg-Kohn theorem, that essentially tells you that for the ground state of a Hamiltonian, there's a one-to-one correspondence between the electronic density and the many-body wave function, or between the electronic density and the Hamiltonian. So the arrow in one direction is, of course, trivial. So from the wave function, you can, of course, always compute the electronic density. But in the other direction, it is not so obvious. But what is important is that this mapping does exist. And so in practice, you can actually think that the ground state energy is just a function of the electronic density. So in principle, there should be a function that allows you to compute the ground state energy from the electronic density, and that it allows you to map, let's say, an external potential to the electronic density. The actual problem in practice is that we do not know what this mapping is. So we know that it exists, but we don't know what its mathematical form. So the way in which this theorem is useful is just by thinking about an imaginary gas of electrons. So the exercise that one makes is that, well, we don't know what is the original functional that relates the Hamiltonian to the electronic density or the electronic density to the energy, but we could think about some imaginary electronic system that has the very same density as the real system, but whose functional we can write down. And the way in which one writes down the functional for this imaginary system is just by writing something that is very similar to a mean field theory plus some correction. So we take this imaginary electron gas and we say, well, now we are going to have kinetic energy for our imaginary electrons. We are going to have something that looks like a mean field, let's say, electronic interaction. And then apart from this, we have another term that is defined as whichever term we have to put in this functional so that this relationship is true. And this term is what is called the exchange and correlation functional. Of course, we also do not know what is the form of this functional, but the motivation for actually doing this decomposition is to actually hope that this functional is easier to parameterize than the original functional that we have from the Hohenberg-Kohn theorem. And the bottom line is that there are several approximations to this functional that have been proven to be very successful in describing actual materials, and some of them are the local density approximation, general gradient approximation, meta-GGA, and so forth. But of course, one of the important questions is, well, we do not know the exact functional. So could we actually use machine learning to learn the real functional? So the idea is that in general, in the Kohn-Sham equations, you have these different three terms in the Hamiltonian. And in particular, for the exchange correlation term, you can always use, let's say, many different approximations. In practice, what you have to do to solve these equations is to take your imaginary electron gas, whose wave function is just a product state. So you assume that this is well described by independent electrons, and then you solve this problem in a self-consistent manner. So your, let's say, wave functions depend on the density, and the density depends on the wave functions. So you put a very specific electronic density at the beginning, you find what is your functional, and then you minimize this. And the way in which you minimize it is, of course, by doing a functional derivative. And in particular, let's say when you do the functional derivative of the exchange correlation energy, you get something that is called the exchange correlation potential. But this object, you of course also do not know it. So the idea is to use machine learning combined with, let's say, different approximations of this potential and see if you can actually find a good approximation to it. And what happens in practice is that you can actually find good approximations using machine learning. So in general, if you have a specific functional for this, the functional theory, you need to find you need to solve the eigenvalue problem. So you have an effective Hamiltonian for your density functional theory that has single particle wave functions. You need to find what are the single particle energies. And in practice, you need to do this several times until, let's say, you fulfill the self-consistent condition. The way in which that is done in practice is by combining different exchange correlation functionals and using machine learning to essentially choose what is the best combination that it's consistent with what the algorithm was trained of. Of course, there's actually a much more bold idea for using machine learning, which is essentially based on the Hohenberg-Kohn theorem itself. So we know that there's actually a mapping between the electronic density and the ground state energy. You can think between the electronic density and the Hamiltonian of the system. The way in which it is usually done, whether if you use a very specific exchange correlation functional or a exchange correlation function that it's parameterized with a neural network, is by taking your electronic density, putting it in the Hamiltonian, then solving your ground state vectors and so forth, and doing this loop many, many times. And in particular, for doing this loop, you actually need to diagonalize the Kohn-Sham Hamiltonian, which is a very, very challenging problem. This problem is, of course, not overcome, even when you parameterize your exchange correlation potential with a neural network. So the question is, can you actually use machine learning in a more, let's say, bold way? So in practice, you can actually think about just parameterizing the whole mapping between the Hamiltonian of the system and the electronic density. And this is something that it's called machine learning potential, which is a very successful idea in quantum chemistry and condensed matter physics. So the idea is that you take the atomic positions of your system, you parameterize the electrostatic potential of your system, and then the Hohenberg-Kohn theorem tells you that there's actually a mapping between the electrostatic potential and the electronic density. And what you do is you use a neural network essentially to perform this mapping. This neural network is trained with density functional theory calculations based on the Kohn-Sham equations. But of course, you can actually train this network with very, very small systems. And then once the algorithm is trained, you can apply it to much bigger systems. And this idea is essentially based on a combination of the Hohenberg-Kohn theorem and machine learning. Okay, let us now move on to a slightly different problem, which is the problem of phase classification in quantum materials. And the idea is that we can actually use machine learning for dealing with this problem. So in general, we would like to actually use machine learning in order to combine theory and experiments. And usually we have some, let's say, theoretical models that allows us to make some predictions. And then we have experimental measurements. And the idea is that in many cases, it would be ideal to use machine learning techniques to combine theory and experiment. Phase classification is, for example, one of these cases where we can actually use, let's say, theoretical models to train the algorithm and then use those algorithms for dealing with real experimental data. Then the other problem is the problem of actually extracting the Hamiltonian of a system. So not learning its phase, but actually learning the parameters of the Hamiltonian. And this is, of course, something that we can also do by combining, let's say, theoretical models and experimental data. To start with this, let us focus first on phase classification. And we are going to deal with two very specific problems, the case of the Ising model and the Ising gauge theory. So the case of the Ising model is, of course, one of the most paradigmatic cases of phase transition. So the idea is that you have a system in a lattice. Let us think, for example, of a square lattice, and you have spins on each side that are Ising spins, so classical spins. and the Hamiltonian of the system is written in this way. So at zero temperature, essentially the state that minimizes the energy of your system is a state with all the spins up. And then at infinite temperature, you can have either all spins in random directions, and of course the system is not ordered. And the idea is that there's a very specific temperature at which your system goes from an ordered state to a disordered state, and this is what we call the critical temperature. Of course, in certain cases, we would be interested in knowing in which phase we are just by looking at a snapshot of a system. And you can think about this as if you just take a picture of the system. So the system, if it is at a finite temperature, is going to fluctuate in time, but you could try to just make a measurement at one time, see what is the state of the system, and by knowing this state, to know whether if you are, let's say, above TC or below TC. The case of the Ising model is, of course, relatively simple in a sense that we can easily guess that a way of knowing if you are above TC or below TC is by summing all the spins of your system. So if all the spins of the system, let's say, point up, then you are in the ordered state. And if you have 50-50, then you would be in the disordered state. But it is an interesting exercise to see if a neural network is actually capable of doing this. And so the idea is that you are effectively just on a classification problem. And this is not different from the classification of images of cats versus images of dogs. So you have snapshots of the system below TC that would correspond to an ordered state. You have snapshots of the system above TC that would correspond to a disordered paramagnetic state, and you can come up with a machine learning algorithm that automatically allows you to classify phase 1 or phase 2. And so you can just identify that phase 1 is, for example, cats, phase 2 is dogs. And you can use the very same architecture that we can use for classifying images to classify phase transitions. And so the idea is that this is an exercise that is, let's say, relatively easy to do. And you can see that for the Ising model, you can find, let's say, very, very good let's say, neural networks that allow you to classify whether if you are in the ferromagnetic state or in the disordered state. And of course, the phase transition becomes sharper and sharper as you go to bigger and bigger systems. All right, so that was a relatively easy problem. Let us now move on to a slightly more difficult one, which is the case of the Ising gauge theory. The Hamiltonian of the system is also a Hamiltonian in a lattice made of, let's say, Ising spins. But now the trick is that we have plaquette interaction. So instead of having, let's say, an interaction between two spins, we have now interactions between all 4 spins in a plaquette. And so the Hamiltonian of the system essentially looks like this. So minus J, and then the product of all the spins in the plaquette. At low temperatures, it is very easy to realize that the ground state of the system is going to correspond to having all the product of all the spins in the plaquette equal to 1. But what is now important to note is that, of course, all these spins may be up, all may be down, or you may have 2 up and 2 down. And at high temperatures, this constraint is, of course, not going to be fulfilled. So high temperatures, some plaquettes will have +1, some plaquettes can have -1. So in this case, you actually cannot know so easily in which phase you are in the system just by summing up the different, let's say, spins of your system. Because, of course, you can have configurations where 50% up are up and 50% are down that are a configuration at 0 temperature, or 50% up, 50% down, and it is a configuration at high temperature. And so the way to think about this is the following. So you can think, for example, about this very specific configuration that actually has all the plaquettes equal to 1, but you see that you have both spins up and spins down, whereas this other configuration over here has all the, let's say, also 50% up, 50% down, but now this corresponds to infinite temperature. So if you look at these two images, then it wouldn't be so easy to actually write down a simple algorithm that it's capable of distinguishing between both. So in this case, you can actually argue that using a neural network can actually allow you to solve a problem that otherwise would be challenging. And in practice, one can actually train a convolutional neural network to classify these two configurations, so to classify both zero temperature and infinite temperature configurations. And in particular, one can use a very similar architecture as in a, let's say, typical image classification problem. Now, the actual trick is that the zero temperature and infinite temperature phases are actually connected by a crossover that is essentially size dependent. So depending on the size of your system, the temperature at which you go from one phase to the other changes. What this actually means is that there's actually not a real phase transition in this model, but it's more of a crossover. And in particular, this model has a topological phase transition. So the high temperature phase is topologically equivalent from the low temperature phase. The important point is that machine learning actually allows you to capture this crossover, let's say for all different sizes and all different temperatures without actually having to train in all of them. So you train with a very specific size and it allows you to predict all of them. Now, to move on, let us focus on a very specific problem that involves also experimental observables and theoretical models, which is the task of Hamiltonian learning. So a very important question in quantum materials is, how can I know the Hamiltonian that describes a system? Usually, when you make experiments, you never have access to the wave function. You only have access to specific observables. And the idea is that with those observables, you would like to know what is the Hamiltonian that governs your system in order to know whether the system has a very specific superconducting order or whether the system has a very specific magnetic order and so forth. So the idea is the following. So usually when we think about quantum physics or quantum materials, the usual task for us is to take a very specific Hamiltonian of a system, and then with this Hamiltonian find observables of the system. And these observables can be the density, can be the magnetization, can be a response function, or something else. So we usually start with the Hamiltonian, and then we go to the observable. But if you think about the actual problem that one has experimentally, when you actually measure a material, you very easily realize that it is actually the inverse problem. So you don't start with the Hamiltonian, you start with a specific observable. And this observable can be the electronic density, this specific observable can be conductivity, specific observable can be, let's say, some ARPS measurements or neutron scattering and so forth. And then from that very specific observable, you would like to have a Hamiltonian that allows you to understand what are the properties of your system. So this, in a way, is an inverse problem. Our techniques from quantum physics and condensed matter physics allow us to go from the Hamiltonian to the observable. Now we want to make the inverse step. And the idea is that the inverse step can be actually done with machine learning. And so the idea is that very often you have, let's say, many different, let's say, Hamiltonian that can be compatible with a very specific set of observables. And these parameters in the Hamiltonian can be, of course, let's say, magnetic fields, can be electronic hoppings, can be many body interactions, and so forth. And apart from that, you may also have some parameters that you are not truly interested. These parameters may be, let's say, some small additional parameters that you actually do not want to know, or that they are not even well defined. This can be disorder, could be actually related with computational limitations of your simulation methods, or just pure randomness in your system. And so the idea is that very often we do not have a lot of theoretical data, a lot of experimental data. We may have as much experimental data, as much theoretical data as we want, but the amount of experimental data that we have is very limited. And so what we actually want to do is to have an algorithm that somehow takes some very specific observable. Let us imagine, for example, a spectroscopy of a two-dimensional system. And with this spectroscopy of a two-dimensional system, we put it inside of a neural network, and then this neural network tells us what are the parameters of the Hamiltonian. And if you think, for example, that your two-dimensional system was a two-dimensional quantum magnet, then you could get the first neighbor exchange, second neighbor exchange, and third neighbor exchange. This is a task that you want to do. And of course, in practice, you would like to do this with experimental data, which is the most common case, or the most, let's say, impactful case. But since you have limited experimental data, and for experimental data, you can actually not train your algorithm, the way in which we usually do this is by taking a technique that we developed to, let's say, simulate the observable. And this observable can be, of course, the local density of states, or the magnetization, or the electronic density, or some spin excitations, or any other type of excitation. We put specific parameters in the Hamiltonian. With this Hamiltonian, we, let's say, predict the observables, and then we essentially train the neural network with these theoretical predictions. We put a very specific we put a very specific parameter, we obtain a very specific observable, and then we train the network to predict the original parameters. And as we do this many, many, many times, eventually we converge to an actual neural network that is capable of mapping the observable to the parameters of the system. And with the trained algorithm, we actually use the algorithm with experimental data. So we take a very specific experimental observable that is the same as the one that we use for the training. We put it inside the neural network, and this essentially allows us to predict the experimental parameters of the Hamiltonian. So as a summary, I would like just you to remember that methods from quantum many-body physics can actually be used in machine learning, and the most paradigmatic example was the case of tensor networks, that we can actually use also methods from machine learning to solve quantum many-body problems. And of course, one of the most important examples with neural network quantum states, and that machine learning methods can be combined with conventional methods for quantum materials. And that this approach allows us to solve some open problems, including the problem of Hamiltonian learning.